welcome back. Let's learn about deep networks and gradient flow in Module 33 of this course. So by the end of this module, you should be able to explain what gradient flow means in a deep neural network and how it relates to the chain rule. This is deeply connected to the very previous module in this course. A bit of a stretch goal, and maybe one that we're only going to kind of touch on somewhat at a distance, is the ability to write down the backwards recurrence for gradients in a multi-layer network using Jacobians. We're going to flag them as being Jacobians throughout, but we don't have to go too much in depth, I don't think, in this module. You'll be able to analyze how depth and activation functions affect gradient magnitudes across layers. You'll be able to implement and inspect gradient norms in a small PyTorch neural network to try to find any early hints of instability in the training process. And you'll be able to, at least to some extent, diagnose simple failure modes where a neural network is technically training, but the gradients have vanished or exploded, causing all kinds of training problems. So here's our big picture. What is gradient flow? And we've already talked about this in a previous module, but let's just make sure we understand it. When we train a network, and again, the implication is neural networks, but it doesn't have to be necessarily. But when we train a network via gradient descent, this will mean that we compute a loss fancy L on a batch of data. So the loss function is going to be a function of our parameters theta. We're back to using theta for our parameters. And a batch will be some subset of the overall data that we're going to use in the training process to make it a bit more efficient. We saw batches in a previous module. To do gradient descent, that means computing gradients. So this nabla symbol subscripted by the parameters just means that we're taking the derivatives of, in this case, the loss function fancy L with regards to the parameters theta. And we know, we've seen this many times already, that this gradient descent method is an iterative process. We take a step and we keep on taking steps as we're moving down through these manifolds of the empirical risk. And we take a certain set of parameters, like our current set of parameters. We subtract from it this term, which is the product of our learning rate eta with the gradients that we're computing for our current settings of theta. And then this gives us a new setting of theta at the next iteration, and we keep on updating the thetas, computing new gradients as we move until we're satisfied that we've trained effectively. Let's see. One thing I wanted to mention here is that it's possible that in this module we're going to trip over something that might be a little bit tricky. And that is the difference between what I'm calling fancy L here, which is what I called the loss a few moments ago. So the first thing is that I'm starting to do what you see an awful lot of in machine learning, which I'm conflating the notion of loss, which is really an error on a particular point, like a difference in a prediction for a particular point. That's the loss, to be differentiated from the empirical risk, which is a measure of like generalizability. It's sort of a probabilistic claim about what's going to happen in the future. Initially, we computed empirical risk over all of the data. Now we're starting to compute empirical risk over subsets of data, over these batches. So the first problem is that sometimes I'm calling what is essentially empirical risk a loss, and it's easy to do this because it's indicated by this this variable L, which seems to stand for loss. So hopefully you'll get from the context what I'm talking about. The main thing I wanted to mention, though, is the difference between fancy script L here, which is I'm now calling loss, and this regular Latin-looking L down here, which is the number representing the last layer I have in my deep neural network. So if I have 100 layers in my neural network, big L over here would be 100. And unfortunately, it's likely, I have to make sure, I haven't checked every one of these, that occasionally I'll be using these two variable scripts interchangeably. So I might use a big L, like down here, to mean empirical risk or loss. That's that. I did go through these slides before. I removed fancy script L as being a reference to one of the layers of the neural network, and I replaced it with a regular lowercase, Latin script L to avoid confusion. But again, look for the context clues to know whether or not I'm talking about like this is the index of the last layer in a neural network, which is here big L, versus I'm talking about empirical risk or loss, which is a fancy script L. One thing I'll note, just to tie everything together and say that this is maybe a problem that's not a problem, is that usually this last layer in a neural network is kind of extremely closely linked to the actual loss I'm going to compute. So it's not completely perfectly the same thing. So you have to watch out for that. But in a course, often we have to at least make some concessions and speak a little bit loosely sometimes. So it's possible that I'll conflate these two concepts, and I'll try not to. But just wanted to flag that. I spent more time on this than I really ought to have. Back on track. So given all of this, a gradient flow is how the gradient signal from the loss here at the output here will travel backwards through each layer to earlier parameters down here, say to the weight matrix and the biases for the first layer. And this will be governed by applications of the chain rule like we saw through back propagation in module 31. So let's scaffold our concepts again. We have a simple, deep neural network, multi-layer perceptron. It has big L layers. It's fully connected, so every neuron in layer L is connected to all of the layers in layer L plus 1. And we have a simple single input X. So if that's the case, our input at layer 0, our activation at layer 0, A sub 0, is just X itself. For every hidden layer and the output layer, that is layer 1, 2, 3, all the way up to big L, we're going to have a pre-activation. We've seen this many times before. It's just a linear function. It's the activation of the variables coming into that layer. So the activations at layer L minus 1 times the weight matrix associated with us, that's weight matrix W sub L, plus whatever bias we have in this layer, which is B sub L. This will give us our pre-activation, Z sub L, which is just a linear function, but we're going to want to pass this pre-activation, this linear function, into a nonlinear function, which I've called phi in the section on kernel functions. I've called G also in the early description of neural networks, same thing. Passing my linear function through my nonlinear function phi, or alternatively G, and this will give me the activation of layer L, which I'll just then push forward through the network in a forward pass. Eventually, the activation at my final layer, big L, will be the prediction. Now, either this is a regression and this is the actual prediction, or it's like a something logistic regression E, and it's the probability of a class I'm trying to make a prediction on. And then I'll have a loss. Oh, here we go. So this big L was previously script L. I'll try to remember to fix this before I post the slides. But this is like the loss. It represents the loss at the output, which is the difference between my prediction Y hat and the truth Y. Okay. Actually, maybe I won't change this. This is what I'm talking about in my little caveat. This is the caveat to the caveat. This is actually kind of correct, right? So the activation is A sub L, but the actual output of my neural network is going to, like in that last node of the computational graph from the previous module, will be the loss itself. So I might change this, I might not, but yeah, the outcome of like the overall computational graph is going to be this computation of loss, which will then be pushed back through, at that point, through my activation at the final layer and then through everything else backwards. Hopefully that makes sense. If it doesn't make sense, go back to the computational graph picture from the previous module where you'll see there's a node for this loss function. Anyway, some more key notation. We already defined what the parameters are. We defined the states. So the states are my pre-activations and my activations. And now I'll have local derivatives. So the derivative of an activation at layer L with regards to its pre-activation Z is going to be just the like the derivative of whatever the function is. So we know how to take the derivative of the sigmoid function. For example, that's just a sigmoid function times 1 minus the sigmoid function. Different nonlinear functions will have different local derivatives, as represented by phi prime. And then what is the derivative of this linear component, Z sub L, the pre-activation, with regards to its inputs, the activations from the previous layer. This will be from the weight matrix L. So here's the gradients as Jacobian products. So our chain rule here, what is the derivative of the loss function with regards to the activations? Sorry, what is the derivative of the output of my neural network with regards to the activations at a particular like layer L, which depends on the activations that came into it, activations from L minus 1. So this is, again, I can use the chain rule. I can break this fraction appearing thing into this product. It'll be the derivative of the activation at layer L with regards to the activation at L minus 1 times the derivative of L with regards to the activation at L, which is the output of what I'm looking at, which is sort of the function g sub L. So this product is broken down here. This big J sub L transpose, this is the Jacobian, and I think this is more or less the extent to which we're going to define the Jacobian, although I'm going to provide a link to it, I think, a little bit later on, so we won't talk about it much more, but this is sort of a Jacobian is a matrix of a bunch of different derivatives, and it's like a derivative of a function with regards to each of the inputs of that function. I'll provide a link to it later. We're not going to need to go into it too much. Suffice it to say that the derivative of activation L with regards to the derivative of activation at L minus 1 is the Jacobian at layer L. And if we're going to unroll this function using the chain rule, so I have an arbitrary layer L minus 1 I care about, I can unroll from the last layer g sub L, and I can take its derivative with regards to the previous layer, big L minus 1, and then I can apply the chain rule backwards all the way back to the original input at layer 0. Hopefully, as you can see from this the chain rule, I can just unroll things all the way to the end, and I get this overall function which describes the function g sub 0. That means the function g at layer 0 in terms of the Jacobian at layer 1, 2, 3, 4, all the way up to big L, and then the output at layer big L. In other words, the gradient at the input early layers will be obtained by multiplying many of these Jacobians together. Okay, so I have I have all these gradients that go from my big layer at the end, big L, all the way back through the neural network, through these multiple products, multiple multiplications, all the way to the beginning. The more layers I have, the more of these Jacobian matrices, shown here by this derivative, I have to multiply together. So the overall gradient flow will be controlled by the product of many linear operations. These are just products of matrices. So these are linear operations. If the typical scale is slightly less than 1, if all of these Jacobians are just like 0.8, 0.7, 0.5, then you're multiplying all of these small numbers together. And if you're multiplying numbers between 0 and 1 together, you're going to get a diminishment. The product is going to get smaller and smaller and smaller, so it's going to shrink. If the scale of these matrices are a little bit bigger than 1, and you're multiplying all of these numbers together that are all bigger than 1, then it's going to have the opposite effect. Then the product of all of these matrices whose scale is slightly bigger than 1 will get bigger and bigger and bigger. I'll define scale a little bit more in a bit more detail in a moment, but you see the overall trend. If these j's were just scalars, and these scalars were small, multiplying them together would diminish to nothing. And if these were all scalars that were bigger than 1, you multiply them all together, the product would get bigger and bigger. The same concept applies. We're just multiplying matrices together. These matrices are described in terms of sort of parameters, which describe their size or their scope, and the same logic applies to products of matrices. And we'll see what I mean by scale and scope in a few moments. So this is what deep neural network is sometimes like. This is usually the full game in a lot of courses of this type. We'll have an input, activation a sub 0, which we defined previously as just our raw input x, and we'll multiply it by a weight matrix w sub 1, not shown as our bias, but it's also here, and we kind of add those together. We apply those to a nonlinear function. This gives us activation at layer 1, and we then pass that activation. We multiply that by matrix, add a bias, pass it through a nonlinear function. This gives us activation at layer 2, and so on, all the way until the very end, the last layer, big L, where we compute our loss. And now we're like, well, I want to figure out like what caused this loss. To do that, I need to compute gradients, and I want at some point, to understand the gradient of the loss with regards to my inputs, and I want to, push these gradients all the way back through this chain, step by step. I know how to do that now because I've seen this graph, so I know that I can take this equation. So I know that I can take the derivative at the last layer with regards to any arbitrary layer L, small l, and I can do that by this chain rule. And depending on where I am in this sequence, I might have to multiply more and more of these matrices together, or more and more of these numbers together. And as I move all the way back to the beginning, I'm going to have a product of a lot of these matrices. These matrices are called the Jacobian, which I previously defined here as the derivative of a sub l with regards to a sub l minus 1. That's basically it. So we already know what an activation is. The activation is like the output of layer L. Every layer will have a different dimensionality, d sub l, the different number of neurons in that layer. A weight matrix from layer L minus 1 to L is this rectangular matrix with L rows and L minus 1 columns. A Jacobian layer I defined a moment ago. And the gradient loss with respect to a particular activation I also defined a moment ago in the previous slide. And the overall loss here is big L. This is the difference between a prediction, the activation at the output layer, compared to a true target Y. So here's our anti-example. We built a 10-layer MLP, so big L. The number of hidden layers is 10. We have sigmoid activations, so at every layer we're pushing pre-activations through sigmoid nonlinear functions. We have a standard normal initialization, so everything is mean 0, everything is variance 1 in terms of our initialized parameters, all of our weight matrices. And we have a very small, like a moderate learning rate eta. And during training, during this kind of setup, which kind of makes sense, our loss is decreasing, which is what we want, but it's decreasing very slowly, or it seems to be kind of like stable, or not changing out of the gate. Maybe our training accuracy will keep on going up a little bit, but then it might stall. So these 2 points are kind of really closely connected to one another. And so far, nothing weird's happening. There's no nans. Our numbers aren't going crazy. Like our parameters are all within regular bounds. Maybe we're also using regularization and so on. Now, however, because we're not happy with how slowly things are training, we go ahead and inspect things. And we find that the gradients at the early layers are going to be on the order of something incredibly small. I'm choosing this number arbitrarily, 10 to the minus 6. Maybe they're smaller, like the actual value of what constitutes a small number or not depends on all kinds of factors, the size of the matrices, the number of matrices, and so on. But you see, like, okay, these early layers, my gradients are very, very small. If the gradients are small, then remember we have their update function, which is our parameters minus eta times the gradients. If those gradients are very small, that second term disappears, and my parameters never change. Eta minus 0 is eta. Sorry, theta minus 0 is theta. So yeah, our early weights are never changing. We're never actually learning anything. This is what we call a vanishing gradient situation. The name should be obvious. The gradient will vanish as we push it back through the neural network. The network is technically training. Our loss is technically training, but almost all of the learning is happening at the layers closest to the output, which I'm calling last right now. They're last in terms of a forward pass. They're closer to the output. The still gradients aren't too small there. We haven't multiplied a lot of Jacobians together yet, so we haven't vanished our gradients yet. So there's still learning happening near the output, but not much in the rest of the neural network. I'm going to talk a little bit about, on building some tools to help understand this problem, to diagnose the problem, and we're going to talk about specific fixes a little bit later. So a bit more math. So we have deep linear networks. I have this board face because we're going back to this pathological situation where we don't have any nonlinear activation functions. We're just doing linear, like everything's linear all the way through. So we'll still have a sub 0 as x as usual. Our activations at layer L will just be the linear transformation of the activations from the previous layer times our weight matrix, like the connections between the neurons. And this is going to be true for all of our layers, from the beginning all the way to our last layer, big sub L. There's no activation function, and actually here there's no bias term either. So our prediction is just going to be whatever number is our last activation on our last output layer L. And here's our loss, which is this 1/2 of the square of the 2 norm of the difference between our prediction and the truth. And one of you mentioned in class several weeks ago, but why do we have this divided by 2 here? That's because we're going to take the derivative of our loss soon enough. Regardless, like we saw earlier, when you have like no nonlinear activations, then the outputs of these neural networks is just going to be a linear combination of all of my weights times the input. Is this going to be, again, a linear function? So again, this is the pathological case where I haven't been able to learn any nonlinear boundaries, but there we have it. This is just for showing you, again, how these problems can occur with vanishing gradients. I want to take my gradient with respect to my output, a sub big L. So here's my loss, here's my gradient with respect to the output. There's not much to it. Actually, here it is right now. So my prediction is just a sub L. So I can replace y hat with a sub L in this loss function over here. The derivative of this loss function with regards to a sub L now is going to be, I can take this overall function. The variable I care about is inside of this little piece over here. So I can take down the 2, which is hidden in the norm, multiply it by everything. 2 times 1/2 cancels out, and I'm left with y hat minus y, or a sub L minus y, which is over here. And now, again, and I have to keep on doing my differential. What is the differential of a sub L minus y with regards to a sub L? That's just going to be 1. And that's kind of hidden over here, and I get my overall function here, which is a sub L minus y. Again, I'm walking you through this, and you might have noticed that I haven't asked you to do derivations of this type on quizzes yet, so you can probably imagine that to be the case going forward. This is not a class in calculus. You should understand what I'm doing, but and you should actually be able to do it yourself, but I'm not likely to give you a hard time about it if you struggle with that. Again, if you have any issues with this, let me know in class. Anyway, we want to keep on pushing things backwards. We want to find the gradient with regards to a sub 0, and we know how to do this. We take our transposes of our weight matrices, multiply it by our gradient at layer L. This will give us a gradient at the input 0. If each weight matrix, W sub L, shares a typical singular value, sigma, read more about it at this paper, then roughly the norm of the gradient at layer 0 will be approximately that singular value raised to the power of L times the norm of the gradient at layer big L. A couple of things are going on here. So I'm kind of washing over what singular value is. We did talk about singular values a little bit when we talked about a principal components analysis, and so we understand that singular value sigma is related to the extent to which each of our eigenvalues represent the overall data. And this we kind of talked about in terms of the stretch of the data in certain dimensions. It's like it represents the scope of data, and then therefore it's related to the norm of the data. This is the scope I was kind of waving my hands at a moment ago. Like the size of the data, can be represented in terms of its singular values. And if there's a singular value, or if there's an average of the singular values, that's all kind of the same. This is what I'm kind of waving my hands at towards in terms of the typical singular value sigma. So you have a matrix. A matrix has a singular values. There's one variable that is kind of representative of the singular value variables. That's sigma. Again, the second thing that's going on here is that, again, this is not my fault. This is how we do it in this branch of science. Sigma is sometimes standard deviation, and sometimes it's singular value. And sometimes it's a sigmoid function. Here it's singular value. Anyway, if each of these weight matrices has a singular value which is more or less the same, So this is a scalar value, so you can raise it to the power of L. You can multiply it by itself, big L times. This is just being applied to this conception over here. This will give you the overall size of the gradient at the input. Okay. Yeah, I think so. Earlier I was talking about a logic of like multiplying together scalars that are small, that are less than 1 together. If you're going to do that, everything's going to collapse into something very small indeed. And the same logic, this is what I'm talking about here. So if your typical singular values for all of your weight matrices are small, if they're less than 1, then coming up with this product will shrink the gradients exponentially with depth until the size of these gradients are potentially very close to 0. If this typical singular value sigma is bigger than 1, if it's big, then as you multiply all of these matrices together, then your gradients are going to get bigger and bigger and bigger and grow or explode exponentially with depth. And kind of what we want is something where the singular values of our weight matrices are more stable, they're more close to 1. So I have a gradient of my loss function at my output layer. These are the changes I'm going to make to my output layer, so a degree of the changes I'm making at the output layer. And I want to push my gradients back through my neural network. I don't want to not learn anything, and for none of the light to reach into the depth of my neural network. I want there to still be stuff for me to do in terms of my weight updating at every layer. That's not going to happen if the gradients shrink, like shining light through deep water. Like we won't be able to learn anything at those deep layers or those early layers. Similarly, if somehow I'm amplifying the light and I'm blinding myself with the light, so to speak, to stretch the metaphor a little bit, or if these gradients are just getting super, super big, then as I'm going to be making changes to my values theta in early layers, theta minus something huge will be like jumping all over the place, and as we've seen in a previous module, that will result in a training process that will be very chaotic. So I want my training to be more or less predictable and stable at every layer of the neural network. That is the key thing to remember here, right? So I know I'm going into a little bit of detail here and there. I'm skirting some detail that nevertheless could have been helpful in terms of what I mean by typical scalar value or typical singular value. So I think this is a good level of depth. This is a good stable point where you can understand why it's important to have weight matrices that are structured in such a way that their gradients are, especially as we multiply all their gradients together, are going to be more or less stable even in early layers of my neural network. Nonlinear network. So all of this was for like the linear case, just so we could explain this very simply in terms of the math. If we do have nonlinear transformations here, this can complicate this explanation a little bit, but the overall logic, the overall reasoning is the same, and you can read more about the overall reasoning for the nonlinear case. We have nonlinear activation functions. You can read these papers if you want to learn more. This is not exactly a situation where I have the microscope and I'm talking about an aside here. Like maybe some details are more important than others, but I guess certainly the overall notion of wanting gradients to be stable as I'm multiplying all of these weight matrices together, all these gradients together, is crucial. So what is the overall role of activation? So in general and in reality, normally we have a pre-activation which is linear, but then we pass this through a nonlinear function phi. If that's the case, then the Jacobian, which I previously said it's the derivative of the activation at layer L with regards to the activation at layer L minus 1. This is going to be defined this way. It's the diagonal matrix of the derivatives of the activation function phi with regards to their, or given their pre-activation, times the weight matrix that went into this pre-activation. I maybe can go into more detail here in a future module, or maybe in one of our labs, or maybe even in the notebook, which I haven't finished putting together yet for this module. But hopefully this is not going to be too complicated. We know sometimes that when we have to take a derivative of some nonlinear function in which there's another function, like a function of g, which takes function f as input, and then that input, the input of f is x, and I want to take a derivative with regards to x. I have to take the derivative of g first, and then I take the derivative, multiply that by the derivative of f with regards to x. That's what's kind of going on here. I'm taking the derivative of activation function with regards to z, and then I'm taking the derivative of z with regards to the activation, which gives me this weight matrix over here. So nothing fancy going on here. I'm kind of skirting over the idea of why is this a diagonal matrix. I'm going to link at some point to a Jacobian in the slide deck, or possibly the next one, where I explain why this Jacobian at layer L is defined in terms of the diagonal of this input, but it's not important for you to know. And in fact, even the fact that it's diagonal is good to know in real life, but it might not come up very, very often in exams and so on. But this is how we define the Jacobian for the nonlinear case. So if that's the case, then the gradient flow, so this transpose of this Jacobian, which we're going to use for pushing gradients backwards through the neural network, is going to be the transpose of our weight matrix times the diagonal of the derivative of the activation function with regards to z sub L, or given z sub L. And this will give us magnitudes which are actually well understood. So the absolute magnitude of remember the sigmoid function goes between 0 and 1. So for most of the inputs we're going to see, you can describe like what the derivative of the sigmoid function given any z is going to look like, because we know what the derivative of the sigmoid is. Generally, it's going to be less than 0.25, or less than or equal to 1 in the tanh case. But this is often going to be much smaller in regions where there's a high degree of change, like in a sigmoid function where the change is changing rapidly. We'll leave it there, but we understand what the typical magnitudes are going to be for the derivatives of nonlinear activation functions sigmoid and tanh. If you multiply, some like 1/4 by 1/4 by 1/4 by 1/4 with each other, then this is going to shrink the gradients. Along comes ReLU. So remember, ReLU was this this function which was 0 when the input was 0 or less, and then it was equal to whatever x was, the linear function. The derivative of ReLU is a little bit more complicated, but it's either going to be 1 or it's going to be 0. So it's not like globally differentiable, but it still works in our context here. The derivative of the ReLU activation unit is going to be 0 or 1. So speaking loosely, half of the units might be zeroed out, and the other will pass like the gradient unchanged, which is a little bit of what we want and a little bit of what we don't want. Sometimes zeroing out parts of our learning process can be helpful from an efficiency point of view. But on the other hand here, if the derivative of the ReLU for z is just going to be 1, or it's going to be like the function itself, then we're not changing our gradients. This is very close to 1 indeed. And then we have leaky ReLU or GALU, which I think we mentioned previously when we talked about neural networks. This will also keep the gradient paths kind of alive. It won't shrink. So it'll have the same general benefits as the ReLU activation function. So one thing to remember is like the depth of our layers plus the activation derivatives, like how these derivatives actually behave. Sigmoid doesn't behave very nicely for us right now, in terms of its magnitudes. And then, of course, the weight matrices, and how these weight matrices W will scale in terms of their singular values, in terms of their size, so to speak. All of this together will determine whether gradients will survive to early layers. Okay, I'll mention that one more time because this is important. I might actually put this into a call out with a big important sign on it too. Obviously, the more depth you have, the more of these matrices you have to multiply together, and this risks having gradients diminish, because the more, again, sigmoid to the power of L, where L is very big, means that you might have a gradient very small. Activation derivatives can have an effect. So sigmoid results in derivatives which are pretty small, which are a lot less than 1. We know that can have an effect on vanishing gradients. Whereas ReLU, the story isn't as clear, but in a lot of cases it won't diminish the gradients as you go layer to layer in the backwards pass. And of course, the weight matrices themselves will have an effect. If the weight matrices are kind of uncontrolled in various ways and have scalar values, singular values that scale their values to an unacceptable extent, this can also result in products that are very small, and that will result in zeroing out our gradients, which is, again, the thing we're trying to avoid. So some examples to hammer home these ideas. Imagine this scalar deep linear chain. We have this toy scalar network to see gradient magnitudes like explicitly, so we're going to be able to very clearly see every detail of this process. We're going to have a forward pass. H sub 0 is x, and for all of my layers 1 to big L, my hidden layer is just going to be some scalar a times h at the previous layer, L minus 1. The output, my prediction y hat, is going to be whatever the output is at layer big L, which is just going to be a to the power of L times x. Again, actually a is not changing layer to layer, it's always the same value a, so I'm just multiplying a at every point of the layer. So I'm ending up with a to the power of L because I'm multiplying a L big L times whatever the input x was at layer 0. My loss is going to be the same one, more or less, I've been looking at before. This is only scalars, so I don't have to take a norm. It's just going to be 1/2 times the square of the difference of my prediction and the truth. Now I can take our derivatives. What is the derivative of L given A? This is the derivative of this whole function. Again, I take down the 2, multiply it by 1/2, it disappears. I'm left with y hat minus y, which is right here. But then I have to multiply that by whatever the derivative of y hat is with regards to a, which I haven't done yet, but here it is. So here is the output. So I just replace y hat with a to the power of L times x. Take the derivative of that with regards to L. I know how to do that. I take down the big L, multiply it over here, and then I multiply that by a to the power of L minus 1. This is like the first form of derivative I take. And all of that is multiplied by this thing x, which I'm treating as a constant now, and there it is. So I'm done. This is totally off the topic, but Lieutenant Commander Data from Star Trek The Next Generation has a daughter called Lal, and here she is in this formula. Anyway, back to reality. So this is the derivative of big L with regards to a is this nice looking simple function over here. So here is just some code for us to do some synthetic experiments with. I'm going to experiment with networks of depth 1, 2, 5, 10, and 20. I'm going to experiment with different coefficients here of 0.5, 0.9, 1, and so on. A here, again, is taking the place of my weight matrices. Again, so this is like everything. I'm just simplifying everything I just talked about down, so everything's just in terms of scalars. And I'm going to experiment with different values of these scalars. And here is just the function that defines the gradients, which follow, like this line 7 is literally just what I just worked out over here in the math. Again, coding and math are so deeply related to one another. And then I just do the experiments over all of my A values and my different possible depths, and store everything, put it into a pivot table, and let's take a look. So this is these are the gradients. I'm at every point I'm computing the gradients over here at line 16. So these are all of my gradients. I can look at my depths, I can look at my activation functions, and a couple of things sort of jump out. So when I have these very small magnitudes A, like 0.5, and I have a depth of, oh sorry, one more thing. This is the gradient at L. So I have, when I have a neural network of depth L, my gradient is 0.5, but when I have deeper and deeper depths, then I have, the gradient gets smaller and smaller, as you can see going down this first column, keeping A fixed at 0.5, having deeper and deeper neural networks, big L increases, the gradients get smaller and smaller. That is contrasted with when I have a scalar A. Again, A is sort of like here standing in for my weight matrix. And weight matrix has a singular value, which I called sigma, and I talked about sigma being bigger or less than 1. The same logic applies when I'm talking about scalars. So now I have an actual scalar, and the actual scalar is bigger than 1. When I have this situation and I have a gradient, with depth L, which is, 0.5 here, but my scalar is bigger than 1. Again, I'll take this 1.5, multiply it by 1.5, multiply it by 1.5, L minus 1 times, then multiply the whole thing by L. As you can see now, as I get to deeper and deeper depths, as big L increases, then that 0.5 becomes 3.75, which becomes 166.9, and it gets bigger and bigger up to magnitudes of 8 digits. So we're well past the millions, we're approaching the billions now, right? So this is an example of my gradients exploding unacceptably. Here in the middle, where my scalar values A are closer to 1, I either get, actually here I'm still getting, actually at the end here, because I'm still multiplying my gradients by L at the end, so I'm still getting gradients that they still get bigger than 0.1 as I'm growing, but this is a bit more stable. The point of looking here when my values of A are closer to 1 is that my gradients are stable. I go from 0.1 to 2.3 or 0.1 to 700. Latter case, not ideal necessarily, but I'm still in the same, I'm off by an order of magnitude, maybe 2, as I increase the levels L. Okay, so this kind of hammering home 2 points, sometimes you want a particular depth of L, and for various reasons we can get into in future modules. So L won't be something close to 1. That'll be too close to underfitting. I need to have something, a depth that's reasonable. But if I can somehow force my weight matrices, or in this case my scalar A, to be something relatively close to 1, then I'll be happy. My gradients will survive, and I can still keep on doing my weight updates. So here's more or less just a plot of the previous visualization. Here we have different values of A, 0.5 up to 1.5. I have different depths L, and then I have the log of my derivative of my loss function L with regards to the activation, with regards to the activations A. And you can see here's the exploding happening in terms of scalar values A being bigger than 1. I have a massive vanishing when they're smaller than 1, which is the purple and blue curves respectively. This is log scale, so if I were to do this in a linear scale, these would be off the charts. I mean, at least the purple one would be off the charts. Again, you can do the experiment yourself and not plot with the log scale, which I'm applying right here on line 6. But yeah, this just kind of visualizes the idea that I've been talking about before. And again, just to hammer this home, when my parameters that I can control, right, in this case it's A, previously it was weight matrices W, or their sizes, their scopes, or their singular values. When these are very small, my gradients plunge as the depth grows. If they're too big, then the gradients blow up with depth. But even in this toy case, the behavior is kind of clear. I want these to be fairly close to 1 for my gradients not to vanish or become crazily big. So again, this is the same idea of the product of many factors that we see in real. This is obviously a toy example. It's a linear neural network, and it's one with scalar weight matrices, but it's this hammers home the point. Here's our second example. Here's gradient norms across different layers. We're going to look at gradient norms per layer in a small neural network with a 2-dimensional toy data set. This is going to be our 2 moons yet again. We're doing binary classification. We'll have a fully connected multi-layer perceptron now with a configurable depth and ReLU activation. So we're also not going to be simplifying with linear layers, but with nonlinear layers. Our experiment is we're actually going to train for a few steps. We're going to do one backwards pass. We're going to record the magnitude of our gradients with regards to the loss for every layer L. Sorry, our gradients of the loss for every layer small l. And then we're going to compare what happens if we have shallow neural networks versus deep neural networks. I should mention at this point, I'm not sure if I mentioned it before, but like what constitutes deep versus shallow is open to interpretation. At the very beginning, a deep neural network was anything with 2 or more hidden layers, and still to some extent, diehards say that, well, a deep neural network can be thought of as any neural network with 2 or more layers. But increasingly these days you have neural networks with hundreds of hidden layers, and it seems that's orders of magnitude more than 2 hidden layers. So is there a difference between deep neural networks and capital D deep neural networks? That doesn't matter so much. In all of these cases we have some hyperparameter, which is the number of layers we have, and we're going to change that to whatever's appropriate given the data we have and given the widths of the neural net of the layers and so on. So a bit of a side note, there we have it. Here's our code for you to play around with this yourself. We have the Moons data set from sklearn. We have our train test split function from sklearn, our standard scalar from sklearn. But now we're going to use PyTorch to actually train our neural networks. So everything's pretty familiar up until line 12. Now we're going to use we're going to use PyTorch, and PyTorch describes its layers in terms of these things called tensors. We had a little brief description of why that is in a previous module. So here we're just describing their sizes. We have X batches. We have batches of inputs X. We have batches of predictions Y, which is our classes. We describe their size here. Here's where we make our neural network. For every layer in depth, we're going to just keep on adding layers to our neural network. So initially we have no layers, and our dimensionality is going to be 2. Our moons just have X's and Y's. And then we're going to append a linear layer, which takes our input dimension. It's going to have an output dimension, which is our hidden layer, as the output for this particular layer. This will be defined linearly, and we're going to call torch.nn.linear, which basically implements the pre-activation, that linear thing we've been seeing in math quite a bit. And then we're going to append at the end of that a ReLU activation function. So whatever the output is from this linear pre-activation is going to be passed to our ReLU. And then these two things together is going to be appended to our layers. And then our input dimension becomes whatever our hidden dimension was at the output of this particular layer. So we're going to add all these layers together. This is done in lines 20 to 23. And then at the very end, we're going to append one more layer, which is going to be a linear layer in our input dimension. So I think we're okay. And then we'll return. I also saw in a previous module, torch.nn.sequential just meant you're going to call this, one layer after the other in a sequence. So this is sort of like like exactly what we've been talking about. There's a series of steps, and those series of steps are transformations of input to linear functions, to nonlinear functions, to linear functions, to nonlinear functions through our layers. And hidden behind the scenes here is all of his weight matrices that PyTorch adds for you. We care about the grad norms for depth. So we will make our multi-layer perceptron, which uses our function we defined here. We'll have our loss, which is cross entropy loss, because we're doing zooming out again. Because, oh lordy. Where were we? Where were we? Here it is. So we're doing cross entropy loss because we're doing classification. We're optimizing with the stochastic gradient descent. On our model parameters, we have our learning rate, and we're done. So we're going to do a few training steps. For 5 times, we're going to, again, zero out our gradients. We mentioned in a previous module why we have to do this in PyTorch. It's kind of annoying that we have to do this, but we do anyway. Then we use our model with our batch to produce logits. These logits are our outputs of the neural network. We'll compare that against our true outputs with regards to our criterion, which we defined a moment ago. Then we'll do our backwards backpropagation. We'll get all of our gradients, and this is kind of hidden for us, thankfully, behind this function. And then we'll do an optimization step, and then we'll do this 5 times. And at the very end, we'll do another backwards pass at the very end, and everything else is going to be just tracking our experimental parameters, depth, layers, grad norms, and then we'll just write them out into a table, which is this last bit we're going to do. This last table is going to be a data frame. So I walked through more code than I thought I was going to do, but I think and you can download this, play around with it yourself. That's always the best way to learn these things. I didn't want to skip too much of the depth. It's important to know the math, which is the theory part, and the code, which is still somewhat the theory part. Anyway, these are the gradient norms, the sizes of our gradients per layer in a bunch of different neural networks. So we've actually trained a few different neural networks in our experiment. So we've trained, here we are. So we trained a neural network with depth 1, like 1 hidden layer, 3 hidden layers, and 6 hidden layers. And then each one we've done the experiment. And let's close that off. So here we have these first 2 rows of our pandas describe the neural network with depth 1. There's only 2 layers to deal with, layer 0 and layer 1, the output. And we have our grad norms. Grad norm, the overall size of our gradients, 0.1 in one case and 0.5 in the other. Next, these 3 rows represent the neural network with, these 4 rows, because I have my input layer, represent the neural network with 3 hidden layers. So layer 0, layer 1, layer 2, and layer 3. And then we have our gradients, the size of the gradients. So actually an interesting thing is happening here. We start with a norm of the gradient of 0.15. That goes down to about 0.14. So we're kind of vanishing as we're going backwards through the neural network. Then it jumps up to 0.17. So things explode a little bit. So this could be described as a weight matrix in which the singular value is bigger than 1. That's responsible for this little jump. But maybe it's, again, not too much bigger than 1. It's still relatively stable. Then things drop down. Wait, where am I? Here I am. Then things do drop off quite a bit. My grad norms drop to 0.03. Very small, but still manageable. I'm still learning something. Anyway, jumping ahead, I guess I don't want to spend too much time on this. The trends can continue here. The gradients are pretty small all the way through this deep neural network. And they shrink, they grow, they grow, they grow, they shrink as I look at the norms of my gradients layer by layer through my neural network. So here I'm putting on the detective hat, I'm opening up the black box, and instead of just looking at the loss curves and seeing how well I'm doing in terms of making predictions, I'm opening up my black box, my neurons, my neural networks, my gradients during the learning process, and I want to see, is there any gear that's out of place, so to speak? I like that metaphor, I just came up with it. There's a gear that's out of place when I'm training and then is propagating problems through the training process. I want to know exactly where that's happening so I can take my tweezers or my scalpel or whatever the metaphor is at this point and operate on my neural network. So it's good to look at grad norms in this way and make sure that things are relatively stable across the process. This is a lot of detail, a lot of matrices, a lot of matrix operations and so on, a lot of derivatives, but that fundamental idea is a crucial one to neural network training. You are not just somebody who just copies and pastes some PyTorch code and then runs it and then sees what happens. Maybe initially that's how you get into these things, and maybe initially you just have to become familiar with some of the steps I did earlier in this bit of code, but eventually you're going to open up these neural networks and really and take the magnifying glass and really identify what's going on, which is exciting. Here's just visualizing the gradient norms. So here's my gradient norms. Here's my index layers. So you see, these are linear layers only. So let's see. These are the gradient norms per layer for different depths. I have my neural network of depth 1 in blue, neural network of depth 3 in orange, the neural network of depth 6 in green. Here are all the gradient norms. Nothing much is happening here. This is just a visualization for what I saw on the previous slide. But you can see depending on the depth, there's this overall change in terms of what I expect my gradients to be. And I kind of mentioned a moment ago as I was walking through the table, it might have been better to do it in this slide visually, but you'll see that these deeper neural networks will show smaller gradient norms at early layers in particular compared to later ones. This is generally the case. It's a lot easier to see with this orange one. So my neural network of depth 3, I have big gradients at the layers closest to the output, and this shrinks as I get close to my inputs. And this is a kind of a normal thing that tends to happen when I'm multiplying matrices together. some of which can be smaller than, have singular values smaller than 1. Typically, sometimes there's a U shape, so like sometimes things shrink, sometimes they grow. I mentioned that a moment ago. That's also very typical. This is a function of the Jacobians, as I'm learning through the matrix. This is a symptom, so like so far looking at these weight matrices, I'm not unhappy. Like this is sort of typical behavior, and I'm okay that things shrink and grow as I go along. I'm not too happy that my gradients get pretty small at my 0 layer, but things are still within reason over here. I'm not even scaling by anything. These are the actual gradient norms, which is nice. Future modules will discuss how to fix this if it becomes problematic. So that's basically it in summary. We've talked about focusing, like in the past we looked at like loss curves, we looked at accuracy, precision, recall, and that is important. Like we want to deploy models, and it's going to be, that's fundamentally what we're after. But if you're on the assembly line, or if you're the scientist actually figuring out how these things work, you're going to care about training dynamics. The first thing we saw was training curves. We saw how training, training curves and like training loss curves and validation loss curves would change over time as I'm going through the epochs, and I wanted them to be kind of smooth, and I wanted them to get smaller and smaller and more or less track each other and go down over time. But digging in a little bit more now, are these gradient norms getting close to 0? If these gradient norms are getting close to 0, then learning will be stalling. Again, theta minus eta times 0 will be 0, and my thetas won't be changing. I won't be learning anything. If I'm doing theta minus eta times something huge, then my theta will be changing drastically, regardless of what my learning rate eta is, and my learning will be chaotic, and I won't be learning anything that useful either. That's also bad. So looking at the norms is a way we're going to diagnose these kinds of problems if my losses are not good or my accuracies are not good. And then indeed, are my parameters updating in a reasonable range? This is something subsequent to doing an analysis of the gradient norms. So a good thing to do is to track per layer gradient norms, exactly like I just did a moment ago. Look for layers whose gradients are effectively 0, or suddenly spiking. So if you can look at, again, going back a second, here, like everything's kind of nice and smooth, but if one of these graphs had a sudden spike, actually, and then everything would probably be pretty big later on, or if suddenly dropped to 0, everything would be 0, earlier in the network from there. Therefore, I know that a layer, whatever that happens, that's where the problem is. I need to do something on the weight matrix. Maybe I need to regularize it or do some other modification so that doesn't happen anymore. Again, maybe look at the activation functions. We know that sigmoid functions are easy to differentiate, but then the scope of the derivative of a sigmoid with regards to some input will be like 0.25 a lot of the time, and that's not good for me when I'm multiplying a lot of these numbers together. So maybe something better like ReLU is going to be the solution, just as it was in real life. We're talking a little bit about initialization. So sometimes how we set our weight matrices initially will actually help solve the problem. And then again, just like if my gradients are vanishing at very high depths, I can maybe make my neural networks a bit shallower and regularize in that way, and that will help not to have vanishing gradient problems. So I think, again, this is a technical thing, but there are downstream consequences. The first one is silent failures. A network with vanishing gradients can still produce outputs that look plausible, but will be undertrained. I have like 100 layers, and my gradients at the layers close to the output are still relatively high, so I'm still learning lots of stuff at layers like 80 to 100. So my loss functions are going to go down in both training and validation, so everything kind of looks fine. So then I'll ship it. But then what I'm doing is I'm shipping a neural network with like 80 layers, which haven't learned anything. Find the neural network is doing reasonable things, but also have a lot of neural layers that haven't adapted. Therefore, the behavior will be a bit weird on new inputs. So what am I even doing? At the very least, I have a neural network that's grossly inefficient. So it's always better to, before you ship things, start looking at the gradients, so that you're not shipping something horrible. In safety critical domains like healthcare, finance, justice, and actually almost everything these days, this can mean false confidence in a model. Like you say, this model is great. Look, the loss curves went down. My experiments were set up carefully. I did cross-validation, but it's still bad in some ways. So don't be overly confident, especially in safety critical domains. If you have poor gradient flow, this can also make models harder to interpret. I wave my hands a little bit at the fact that different layers can represent different levels of abstraction for meaning. And again, if those early layers haven't learned anything, they haven't abstracted anything, they don't mean anything. So if I want to look at the layers in a prediction to try to explain what's going on, if those layers are kind of chaotic essentially, then they don't mean anything. If I try to explain something, it'll be spurious and therefore nonsensical. And then, so systematic gradient diagnosis. This is something that's part of responsible machine learning. Often when we talk about responsible machine learning, we're talking in high-level terms about bias, about privacy, and so on. But it's also a technical challenge. We need to open up the neural network and make sure that good things are going on in the process everywhere. It's not just, everything I mentioned before is not just mathematical curiosity. It's super important to be a responsible machine learning person. So there's a lot of curiosity here. So this is stuff that's not in the exam, just a curiosity for you to look into. Residual networks, or ResNets, add these things called skip connections, which sort of go from layer L to some other layer L plus something else. We'll skip layers in order to pass information forward. And then therefore the gradients will also tend to be a bit bigger and avoid areas where you might end up vanishing some of the gradients. That'll allow you to push information backwards through supermassive neural networks a lot more effectively. We're probably going to see ResNets when we come to computer vision later in this course. There's variance preserving schemes, such as Xavier Glorot, I can't remember how to pronounce these names, and Bengio. So there's initialization for activations that are designed so forward activations and backward gradients are not going to diminish. So there's ways of initializing your training in a way that is beyond this particular module. This module is all about the symptom, not about the cure, but there are cures out there. And the cure is because of the symptom we've been talking about, which is why we have this connection. We have normalization layers. At every layer, we've talked about pre-activation Z, like this linear function. We've talked about activation functions like G or phi, these nonlinear functions. But there are ways of normalizing over batches or normalizing layers. And there's these papers that describe these a lot. And when we do coding, we'll often have these lines doing normalization. I think we're going to see these in the very next module. We'll see them soon enough. That indirectly stabilizes gradient flow and will make deep optimization robust to the kinds of problems we've been talking about. And then certainly in transformers and beyond, these will have all these attention mechanisms, which will also have very small numbers, which have to be multiplied together in ways that vastly diminish things. But there are ways to stack these gradient-friendly design choices, similar to the ones we've talked about, layer norms, residual connections, put everything together in one big batch so that you can train with these modern transformers, which we will see later in this course also. So most of the standard architectural tricks in deep learning, some of the things you end up learning how to do by hand or manually as part of your practice. Skip connections, principled initialization, normalization. These are motivated by the problems we've been talking about today. Here are your quick checks. No mathematical weirdness I can see, thank goodness. Here's our summary, which I kind of felt I've gone over before. I'll go over it again. Every neural network you've seen so far in this class, and probably all those you've heard of, it sounds like Carl Sagan. Every neural network you've seen, every neural network you've heard of, runs on one core idea, the reverse mode autodifferentiation or backpropagation. The forward pass, you provide inputs, you get a scalar loss at the output through these things we've characterized as conceptual computational graphs. And we've cached our useful intermediates along the way. The backward pass will assign penalizations. For this output, you have a big error, you have to assign the blame. This will be done through pushing gradients as messages back through this graph, through these chain rules we talked about last time. And every node will have to locally compute how much did I matter to this error overall. But doing this, we'll push gradients, for potentially millions or billions or even trillions of parameters these days. But if you do so in the ways we've been describing, the cost of a backwards pass will be roughly approximate to the cost of a single forward pass. The bottom line here again is how do you feel about this? I don't care about your emotional feelings too much, but why does this all matter? Backpropagation obviously matters because it's a training algorithm behind everything we care about in image, large language models, diffusion models generally, game playing agents, etc. So I call it a superpower, but like this is it. So like a lot of people who don't take this course or don't get into it the way that I'm encouraging you to, will just call backward and leave it at that and say, this is the training thing. I've done training because I wrote dot backward parentheses. So they think they're doing machine learning, but you, at the very least, know about exploiting and vanishing gradients, and you know that there could be a problem. So you know that you can open up the neural network, look at the norm of the gradient at every layer, and you can spot to see if these gradients are diminishing to zero or spiking. And so far, I've hinted that there are solutions to these problems, but at least you know more than everyone else knows. You know where problems can lie, so you know how to diagnose them. And you also know a little bit about the idea of a computational graph, so you can kind of conceptualize a little bit of what's going on under the hood, as opposed to this big cloud of neural net nonsense, like everyone else who does not take this class might incorrectly think. Here are some really lovely papers I advise you to read. Thanks so much. See you next time.